for point A, this is a pen, so I could just simply choose AX and AY. I mean, I could choose going this way as well as this way. So I just chose the positive directions. That's just for this point.
But wouldn't dy be in the opposite direction if dy and ey are opposite of each other?
You mean these two?
No, since dy and ey are opposite of each other, wouldn't forces at A and forces at B be opposite of each other too?
See, when I was drawing the free bodies for these, I had the choice to pick any direction. So I picked these two, okay, and then I picked this going out arbitrarily. Same thing here. The D, I had a choice. So I picked dx and dy going positive. This one, I just made a choice that it goes down. I mean, there's nothing, if I change this thing going up, it's not going to do anything.
It's not going to change your answer?
No.
Okay.
I mean, it'll change the, if you do a calculation for ey, and if it's going down here, and that's where it's actually supposed to go, then when you do calculation for this, it'll come out positive, okay? But if you make it go up, then it'll come out negative. But when I made this choice, I had a choice to choose going up or down. I just chose arbitrarily. I mean, there's no what you call rational reason behind choosing this down.
Okay, then it won't change your answer.
When you come here on the arm, then you have no choice left.
You've got to go the opposite.
At this point, if I chose that the forces at the jaw are dx this way and dy this way, it's the same identical point on the arm. So the force which will be on the arm has to be exactly in the opposite direction. So, for example, let's say if I would have chosen this going this way, at this point doesn't matter. You have the choice. You can make it go this way. But when you come here, the choice is gone. It has to go this way. So if I chose this thing to go in that direction, this has to go in that direction. The choice is no more there. Okay. Now point C, there is a choice. I mean, there is no C here. So whether I make it go this way, or I could make it go this way and just leave this thing going up. That won't affect anything. But when you come to B, again the choice is gone. Because this B is going up, that means this B has to go down. It's the same identical point. One force is on the jaw, and this really is the force exerted by the jaw on the arm. And that force will be exactly, I mean, it's going to be always opposite to what you have here. So that was one point, that you don't need to solve every single force in your problem. You just work your way backward and then see what you need. Because some of these problems get really long. You have too many forces in those. But if you make correct choices on the equations, then actual solutions are very small. I mean, look at this problem. How many equations you need? A total of 4. But if you went blindly, you're going to write 3 equations here, 3 here, and 3 here. You're looking at 9 equations. So that's something you have to get used to, or at least do some practice on how to properly choose what part of the free body diagram and what sets of equations are that free body diagram. And as I said, the best thing to do is you work your way backward. Once you start from here and you see that this is what I need, so what do I need next? You say I need all of these. Then you see out of those which one are really absolutely needed, and then you go backward here and see how you can get those. In fact, static, that's the best strategy for most of the problems. First you look at what do you need, and then you work your way backward of what you really have to do to get those values. Okay, that's one aspect of it. The second thing you will have noticed is the magnitude here. You see, P is 50 pounds. And if I go all the way up here and look at this, you have the actual force is 450 on the wire. So there is a magnification. I mean, to get a force of 450 pounds, all you need to apply is a force of 50 pounds. So there is a gain. I mean, you're applying less force to actually get a higher force at the point of where the wire is being cut. So this ratio, which is 9, or you could say 9 to 1, that's the gain or amplification. And this is also as a result of what we call as the lever action. I mean, maybe this problem looks very different, but it's no more different than something having a force P1 here, another force P2 here, and you have, let's say, an arm as length L1, another at length L2. So your force here is going to be considerably small compared to what you have here, and the difference will be decided by the ratio of these two lengths, which means L2 over L1. The larger is L1, the smaller will be the value of P1, right? Because if you take moments about this point, you get P1 L2 equals P2 L1. I mean, this point was A, and if you would have summed your moment about A, that should have gone to 0. So your P2 would be P1, that's your force, and L2 over L1. So this ratio is really the same number here. And I mean, you could see even if it looks different, what do you have? This is your center. On this end, this is the force you're trying to balance, and then these two forces are balancing it out. So that gives you a factor of 9 to 1 gain on this system. And that's primarily what we call as the advantage of designing machines, that you apply a very small amount of force from your own end, but the place you can actually amplify the pressure or the force. Okay.